Welcome to the next lecture on the pulse shaping filters. In last lecture, we studied that to avoid intersymbol interference, we need that the filter, effective filter uh, response should be one of the possibilities is to have impulse response as sinc function sine of pi t by ts divided by pi t by ts. Okay, but we also uh, told in that lecture that there are several problems. One is that it's a non-causal system. The other is that it has a very sensitivity with the sampling. If there is any non-synchronization in sampling period, then there can be lot of mismatch in the symbols. Now practically now what is the this is the time domain response, and the frequency domain response of this filter is simply rectangular function. Okay, now there are uh, different filters for shaping the pulses before they are actually transmitted over the channel, so that we avoid the intersymbol interference, out of which one of the famous is the raised cosine roll off filter. This is very popular, and it was used. It's not used now. It maybe in old systems. So it was used in some Wi-Fi systems and in older communication models. So it has transfer function in frequency domain as HRC of f. Okay, so it is 1 for a range of frequencies definitely greater than 0 and less than or equal to. There is a factor alpha. This is called roll-off factor. We will see what is its significance. For this range of frequencies, the filter response is 1, and the filter response is having a cosine flavor. So 1 plus cos of pi times 2ts mod of f minus 1 plus alpha. So this pi is throughout common, divided by 2 alpha. Okay, this is for the range of frequencies 1 minus alpha divided by 2ts less than mod of f less than or equal to 1 plus alpha divided by 2ts, and it is 0 for mod f greater than 1 plus alpha divided by 2ts. One thing we will observe quickly here: if you put this alpha equal to 0, now see what will this equation will look like. It will be 1 for 0 less than or equal to f less than or equal to 1 over 2ts. Then what will be this half 1 plus cos of, there will be this 2 ts pi times. Oh, okay. So this term actually, there is alpha in the denominator, but what we observe is you just if you don't evaluate this term first, but you observe when you put alpha equal to 0, this range will disappear. Why? Because when alpha is 0, 1 divided by 2ts less than mod f less than 1 by 2ts, so this range is not there at all. So this term will disappear, and then it will be 0 for mod f greater than 1 over 2ts. If you plot it, so this is mod f, so 1 over 2ts minus 1 over 2ts, it becomes rectangular function. See, what is actually, uh, what is this role of this cosine filter? If you remember that, if you see this rectangular filter earlier, which we saw, whose time domain response will be something like this, right? We wanted two things. One is that these, side bands or these lobes should have minimum effect, and also it should be more steep. So what razor cosine does, the in between part of rectangular, if you plot this razor cosine, it becomes something like this. Okay, so this part is the cosine part, this part is the cosine part, and in this range of frequency it is. So because of this, converting this abrupt jump in filter at this point into the sweep jump, what happens in time domain is that it becomes something like this. Okay, we will not prove it, but you can demonstrate this using some numerical tool of MATLAB also. So for alpha equal to 0, you get rectangular function, and for alpha between 0 and 1, okay, what you will observe is that as you increase the alpha, the time domain response of this filter is such that these extra side lobes, which basically result in intersymbol interference, their role will decrease, their amplitude decreases. Okay, so this is the frequency domain response of, and equivalently you can take the Fourier inverse and you can find a transfer function in time domain also of razor cosine filter, that is sine of pi t over ts divided by pi t, then cos of pi alpha t over ts divided by 1 over 4 alpha t divided by 2ts square. So you are not supposed to derive it, but this is just an observation. So what you will observe, the first part of this is sinc part, but then there is a cosine part which controls the two things. One, the extra side lobes are being controlled, and their slope also is decreased. That is what we wanted. Similarly, there are other shaping filters. One of the famous another shaping filter is Gaussian pulse shaping filter. So it is very it was very popular shaping filter. It was used in GSM. Okay, that is your 2G mobile systems. Even in 3G, it has been used, and it has been used along with something called minimum shift keying. Minimum shift keying modulation. So for time being, you can just take this minimum shift keying as a frequency shift keying modulation technique. So in GSM, what is used is we are using frequency shift keying along with the shape of the pulse is being shaped by Gaussian pulse shaping filter. It has the filter response is given by a Gaussian kernel, that is e to the power minus alpha square f square. So since if you know that the Gaussian distribution looks like this, for that reason it has a shape of bell shape, right? So for that reason it's called a Gaussian filter, and its time domain response is something like this: hg of t is equal to under root of pi over alpha e to the power minus pi square by alpha square t square. This is this time domain. So these filters are used to before transmitting the pulses over the channel, so that it avoids intersymbol interference. Because of lack of time, I will not develop this course more into this direction now, because it needs a lot of time because of my illness and other factors. Now I will start cellular communication. Okay, that is a little bit easy also. So my next lecture series will be on cellular communication. We will first complete the basic design of cellular communication, handover process, and several terminologies of that, and then we will also do the large scale, small scale and large scale fading models in the subsequent lectures. Thank you.